Hello, and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. In this video, we're going to go further with parametric curves and talk about what we can do in terms of calculus with parametric curves. Really, 10.1 should have been somewhat of a review, because 10.1 and parametric curves in general should have been discussed in Math 1060. However, here we're going to now talk about the concepts that we've been working with in calculus and how those apply to parametric curves. First, we're going to talk about how to do both the first and second derivative of a parametric curve, and then also how we would do integrals relating to parametric curves, specifically integral forms that we've been working with, so area, arc length, and surface area. First, the first derivative is actually probably the easiest thing to do. Even if you didn't know what the formula was, you can probably guess this one. If you're doing the first derivative of a parametric function, so you're trying to find dy dx, but both y and x are written in both t, then that means all you need to do is the derivative of y in respect to t and also the derivative of x in respect to t, and put those on top of each other. So what you get here is the derivative of y, or dy dx, is dy dt divided by dx dt. And that's it. That's all we're doing for the first derivative. That's going to be the easiest thing here, but we're going to be applying this in a lot of different cases, so always keep this one in mind. There are a couple things to note, though, about this equation of the first derivative. Notice that we do need to keep in mind that dx dt cannot be 0. If that is the case, then that means the denominator is 0, which is invalid. That's not something that exists. What that actually means, then, if the denominator is 0, is that actually is defining a vertical tangent line, because that means that the slope, which is what the first derivative is supposed to do, is non-existent. That only happens when you have a curve and you have a point where the slope is perfectly vertical. So, if dx dt equals 0, that defines vertical tangent lines. If dy dt is equal to 0, which is the numerator, that means the entire derivative itself is 0, that defines horizontal tangent lines. That's actually pretty handy, because then if we have parametric equations, we don't need to solve for what just the function of y is in respect to x. We could just use those parametric equations and solve for vertical and horizontal tangent lines, or locations of them, a lot easier. So that's the first derivative. Pretty straightforward, but we're going to have to keep this in mind to talk about what the second derivative is. Now the second derivative, remember, the second derivative is supposed to show you where concavity is. So if it's equal to 0, that's where the change in concavity is. If it's ever positive, that means it's concave up, and if it's negative, it's concave down. The second derivative is not going to be as simple, though. You're not just going to do the second derivative of y with respect to t over the second derivative of x with respect to t. It's going to be a little bit more complicated than that. What we're really doing, in essence, is we're trying to take the derivative of what we just did, dy dx. Well, in order to do that, what we really need to do, if we're trying to do the derivative in respect to x, that means what we actually need to do is the derivative of the derivative in respect to t over the derivative of x with respect to t. This should look familiar because this is the same thing as the previous formula. Notice that we did dy dx of y, and that gave us dy over dt over dx dt. Likewise, here we're doing the derivative of dy dx. So that means we're going to do, instead of y, we're going to do dy dx with respect to t over dx dt, so the same thing. So this is going to be our formula for the second derivative. And I already said this, but this does not equal just the second derivative of each of the pieces with respect to t. That's not going to be the same thing. What you're doing here is you're taking the derivative of the derivative you just took with respect to t, and then you're also throwing that over dx dt again. Now, to show that even further of how that's not the same thing as just the two derivatives over each other, I have this expanded out. If you're doing the second derivative, we have the formula above, And when I have part of this in green so you can identify where that piece is going, because that can be kind of hard to understand where that piece is going to be ending up. That dx dt, I'm going to separate that out as just a multiplication of 1 over that fraction, because I'm not going to use it yet, but I want to save it out. Then I'm doing the derivative of dy dx with respect to t. Notice that that means I'm doing a derivative of something divided by another. So I'm doing a derivative of a quotient. Specifically, dy with respect to t would be defined as dy dt, and dx with respect to t is dx dt. This is the first derivative. That's what this formula is, dy over dt over dx dt. That's what the first derivative is. But then if I take the derivative of that with respect to t, that means that I need to do the quotient rule, because I have two things on top. I have one on top, one on bottom. The quotient rule, otherwise known as low d high minus high d low over low squared. We have the bottom, dx dt, times the derivative of the top, so d squared y over dt squared. So it means dy taken to the second derivative, minus the high, the dy dt, times the derivative of the bottom. So that means x with respect to t twice, over dx dt squared. Note that the original dx dt has been separated out, and that's still there. And that means that if I multiply that over again, I have yet another dx dt on the bottom, and I end up with 3 of them. Dx over dt to the third power. This formula here is a secondary formula for the second derivative, really. So it's an alternative formula for it. And it's the one that I'm going to recommend that you use, simply because this formula involves the first derivative, the second derivative of both x and also y. Those are the only things that you're going to need to know to solve this. Whereas the original formula involves dx dt, which you probably already knew to solve the first derivative, but then you have to take a derivative of the first derivative, which may be complicated. A lot of the first derivatives are going to be ugly quotients, which is going to take extra work to do. I think that if you just take the first and second derivative of x and y initially and plug those in appropriately, that'll be a little bit more simple to do. You'll see a couple examples of that moving forward. So that's what I was talking about here, that we have the 2 different forms, and overall, these are the 2 derivatives we've discussed up to this point. The first derivative, dy dx, is dy over dt over dx dt. And then the second derivative, you can either do it in this way by taking the derivative of the first over dx dt, or you can do all the first and second derivatives applied. Again, all of these would be the same. I just think that the second version is going to be better. Also, because the second version will often require less algebra manipulation to clean it up. The first one, when you take the derivative of the derivative, that usually gets ugly, and then you have to divide that by another function. So that gets kind of gross. Let's do a couple examples so you can see how this goes. So for both of these, what we're going to do is find both the first and second derivative of these, and then we're going to determine the intervals of concavity for both these pairs of parametric equations. All right, so here's how I recommend solving these when you're doing derivatives. We have x and y, and what we're going to need in all of these derivatives, both the first and second, is the first and second derivative of each of these. So let's find those first. I have x is t squared minus 1, or plus 1. And so if I do dx with respect to t, that'll give me 2t, derivative of 1 is 0. And then if I do the second derivative with respect to t, I just get 2. Likewise, I can also start off with y equals e to the t minus 1. dy dt is e to the t, and also d squared y over dt squared is also e to the t. These are all the things I'm going to need to solve all my derivatives. Look how easy those were. That's going to be my bank, and now I'm going to pull from those. So the first derivative, dy dx, based on the formula, is the derivative of y over the derivative of x. So that means we have derivative of y is e to the t. Derivative of x with respect to t is 2t. And that's it. That's our first derivative, e to the t over 2t. Now, if you do the second derivative, d squared y over dx squared, if you're doing the second derivative, you could do the first formula, but that means you need to take the derivative of this. Notice that means that you would have to do a quotient rule here again, which gets worse. Why do the quotient rule when we already have a formula that works with that in mind? Here we just need the first and second derivatives. So dx dt is 2t times the second derivative of y, which is e to the t, minus the first derivative of y, which is e to the t, times the second derivative of x, which is 2. All over the first derivative of x cubed. That will give me, if I multiply these out, I have a 2, and one of these 2's will cancel. I'll have 4t cubed, and on top I'll have t e to the t minus e to the t, which you can also factor out if you want. But that is going to be my second derivative. Look how simple that was. If you had to do the original form of the formula, the one that the book likes to present this one, if you want to use that version of the formula, that means you'd have to take the derivative of this, which requires an extra quotient rule. But this is already applying that quotient rule, but just using the easier derivatives you found earlier. Okay. Now what we need to do is also solve for the intervals of concavity. So that means what we need to find first is the value where this will equal 0. That will indicate the change of concavity. So where this equals 0. Minus e to the t, I can even factor that out and say e to the t times t minus 1 over 4t cubed. Well, the denominator is not going to do anything to make this 0, but that t minus 1 is. If I set t equal to 1, then that means I'm going to have this equal to 0. So t equals 1 is going to be my change of concavity. Therefore, I'm going to have two intervals. I'm going to have the interval of t greater than 1, and I also have the interval of t less than 1. And with these, I just need to solve for what concavity they are. Remember, if it's positive, it's concave up. If it's negative, it's concave down. I don't need to do too much testing with this. If t is greater than 1, for example, 2. All right, 2 minus 1 is positive. E to the 2 is positive. 4 times 8 is positive, so these are all positive. Overall, this would be positive, so that means it is concave up here. I'm just looking for the second derivative and seeing if it's positive. If t is less than 1, well then something less than 1 minus 1 will be negative. Something less than 1 here, well, e to the t, this is always going to be positive. And then I have 4t cubed. 4t cubed, if t is less than 1, well, if t is less than 1 and actually above 0, then that means this is going to be positive. So it means the overall thing is negative, so that's concave down. But then we see 0 as a problem because the denominator can't equal 0. But what if t is less than 0? So if t is less than 0, that means that the overall thing is negative, or t is negative. Well, if t is negative, e to the negative number is still a positive number. Negative number minus 1 is still negative. And 4 times something negative to the third power, that will still stay negative. The negatives will cancel. I'll end up overall with a positive number. So this is going to be concave up. So we actually ended up with 3 intervals here. And those are going to be my intervals of concavity. Alright, so that's how we check for concavity. We look at the formula, see where it equals 0. We also had to consider 0 itself in this case because that would be a not equal, another point of discontinuity, really. And so we had to check the other side for concavity. Okay, so that's an example of finding both the first and second derivative and then checking for concavity. Let's do another one of these. So the first and second derivative of these, and then we're also going to find the concavity yet again. So first we have x is t minus natural log of t. And so what we're going to find is the first and second derivative of each of these. The first derivative is 1 minus 1 over t. And the second derivative is going to be, that's t to the negative 1. We'll pull out, that'll actually be 1 over t squared, positive. And then if I have y is t plus natural log of t, I have dy dt is 1 plus 1 over t. And then the second derivative of y with respect to t, that'll give me negative 1 over t squared. That's going to be my toolbox, and I should be able to use those to find both the derivatives. The first derivative is dy dt over dx dt, so 1 plus 1 over t over 1 minus 1 over t. We can leave it like this, or we can simplify a little bit, and all that takes is multiplying top and bottom by t. If we do that, that'll clean it up. I'll have t plus 1 over t times t is 1 over t minus 1. So that's my first derivative. Second derivative. Okay, second derivative. Again, I'm going to use the alternate formula. So the alternate formula is low d high minus high d low. So I want the dx dt, 1 minus 1 over t, times the derivative of the top, which is negative 1 over t squared, minus the other pairing, so 1 plus 1 over t, times 1 over t squared. This is also nice because basically I'm just multiplying these ones. It's almost a cross multiplication. Over the original denominator squared. So 1 minus 1 over t, not squared, cubed, sorry. Okay. Now this will take a little bit. We can multiply these. I'll get negative 1 over t squared plus 1 over t cubed minus 1 over t squared minus 1 over t cubed all over, making sure I got those right, plus plus, minus minus, yep, everything was good, over 1 minus 1 over t quantity cubed. We'll deal with that in a moment. We see this minus 1 over t cubed cancel with that one. Overall, we get negative 2 over t squared all over 1 minus 1 over t quantity cubed. And if we want to simplify this, I have this t squared, but I also have the t down here that's technically going to be cubed. What I can do is, like I did before, multiply the top and bottom by something, And what I'll multiply is t cubed. If I multiply by t cubed, I get t over t squared times t cubed will give me negative 2t overall. And on the bottom, because it's cubed, I can actually multiply the t on the inside here. And what I get is t minus 1 quantity cubed. And that's going to be my second derivative. Okay. So that's overall that. Again, if you want to roll the other way around and find the derivative of this, and then divide that by 1 over t again, you can. It's up to you. Now we aren't exactly done because we also want to find concavity. Looking at this formula though, we have two problems. If t equals 0, this equals 0, which means that that's a change of concavity. But if t is equal to 1, the denominator is 0, that's also going to be a point of discontinuity. So we have to check both of those. So that means we really have three intervals here. We have t less than 0. We have t between 0 and 1. And then we have t greater than 1. If t is less than 0, all we need to do is look at this original formula. So negative 2t over t minus 1 cubed. And what we need to just figure out is what's going to happen to the top and what's going to happen to the bottom. If t is less than 0, it's a negative number. Negative 2 times a negative number is going to be positive. A negative number minus 1 is going to be negative to the third power is negative. That's positive over a negative. That'll be negative itself, so that means it's concave down. Don't even need to plug in a number to find that. Just think about it theoretically in terms of the signs. That's all I need. If t is between 0 and 1, that means it's a positive number. Negative 2 times a positive number is negative. Something between 0 and 1 minus 1 will be negative. To the third power will also be negative. A negative over a negative cancel out. This is going to be concave up. And I can do that one more time. With t greater than 1, it means it's positive. Negative 2 times a positive number is negative. Positive, something bigger than 1 minus 1 is positive. To the third power is positive. Negative over a positive will give you concave down. So that's all we need there. It's concave up between 0 and 1. It's concave down everywhere else. All right. So those are some examples of how to deal with derivatives. Most of this was really the algebra behind it, really. Otherwise, it's still just using the same concepts of derivatives. We're not introducing new derivatives per se. Like we already know how to do derivative of natural log, cosine, whatever functions we have. We could do all those just the same. Now, aside from derivatives, we also can talk about the familiar formulas we've been using since chapter 6 and 8. So area, arc length, and surface area. And we could change these into their parametric forms as well. And doing so actually is pretty easy. All we need to do is consider what the original formula looks like and replace with their parametric approximations. Here we're going to consider x as f of t and y as g of t. I'm going to show how we would typically write both of these parametric equations, both with the dx dt notion, so dt notion, but also with this notation as well, with f and g. Just some people have an easier way with both. First, if we're doing area, we know that we take the area of a curve by just taking from a to b of that curve derived over x. That's all we're doing for area. Well, in this case, then I can plug in whatever function I have for y in terms of t. So y is going to equal some g of t function. That's perfectly fine. But then dx, if I think about that as dx over dt and multiply by a dt, what I get is the derivative of dx dt times dt for my differential. And this is going to be my formula for area. From alpha to beta, which you can find by using x of f of t and plugging in the values of x to solve for these new bounds. You can do that if necessary, although most cases you won't have to. Of the function y times the derivative of x. Or g of t times f prime of t. That's it. That will be my formula for area. Relatively straightforward. That may require some manipulation, particularly partial fractions. This should look like a partial fraction, not partial fractions, by parts, because we have a multiplication of two functions, so you might need to do that, but take it however you need to. So that's how you find area. If you're doing arc length, remember that we have the formula for arc length given us this, from a to b square root of 1 plus y prime, or the derivative of y squared, dx. Well, y prime we consider as dy dx, and we can replace dx using the same trick we did before. And dy dx, from the first page, the derivative of y over with respect to x, if I do that with parametric, I have dy dt over dx dt. That's the first derivative. And that is squared. Then, this dx dt, if I move that into the square root by making this the square root of dx dt squared, that will multiply 1 and make dx dt squared, and multiply this dy dt over dx dt and cancel out the bottom and just make it dy dt. So that gives us our formula for length. The square root of one of the derivatives squared plus the other derivative squared. This one, the order doesn't exactly matter because it's addition, and addition is commutative and associative, so it doesn't exactly matter the order here. Or if you want to put this in f and g terms, f prime of t squared plus g prime of t squared, dt. That would be arc length. And lastly, surface area. Remember that surface area is basically like the volume formulas and also arc length. It has the same arc length part in it. It has this square root of y prime squared dx. So I'm just going to straight up replace that square root with what we found from the arc length formula. And then y we can evaluate just like we did with area. All I would do is plug in the formula for y in respect to t. So that's going to be the y equals g of t formula. And that's surface area. It's already solved because we know how to do area and arc length. Or if you want to write it another way, g of t times the square root of f prime t squared plus g prime t squared. So those are some of the formulas we've been working with and how they be written in parametric. I have this table here that kind of sums up everything. We have the Cartesian forms, what we've been working with in chapter 6 and 8 for these two, and then the parametric forms. I believe I also brought these up in the lecture notes before, but now you also have them side by side as comparisons. Okay, I personally prefer this method over the f prime and g prime notation, but it's up to you really. So that's why I have this method here. I think it's a lot easier to compare back and forth. Alright, so we have a couple examples of these, but just note that moving forward, we are going to have more forms of this, not just parametric. We're going to add polar to this in terms of how we'd evaluate polar coordinates. Although polar coordinates are basically just another parametrization method, so they're going to look almost identical, if not the same. So let's do a couple of equations here. The examples I chose here are a little bit nasty. They're not going to solve very cleanly, but I find them to be fun because, yeah, they don't solve cleanly. If it's too easy, it's not interesting. All right, here we're going to find both area and arc length of the parametric curve defined as x equals t sine t, y equals t cosine t, comma, and t is between 0 and 1. Okay, so we're not finding surface area. We'll do that in the next one. Okay, first area. Area is actually going to be the tricky one here. So area from the previous formula is y dx dt dt, and 0 and 1 are my bounds. So then, y is t cosine t, and the derivative of x, we can find that. We're also going to need the derivative of y in a moment, so why not find both of those? Dx dt, that will give me, by the product rule, that will give me sine of t plus t cosine of t. And dy dt, derivative of y with respect to t, that will give me cosine of t minus t sine of t. So those are my derivatives. I could plug that derivative in here. We get sine t plus t cosine t dt. Okay. I'm going to try to see if I can curve my t's or something so they look a little bit different than my pluses. So something like that. All right. This, if we expand that out, I have t times cosine of t sine of t plus t squared cosine of squared t dt. All right. Now, these we're going to have to split up a little bit further, so I'm actually going to split this up into two integrals, because these are going to be solved in a different fashion for each. So t squared cosine squared t dt. This one is pretty nice. Cosine times sine, you may have had this on your homework, but cosine times sine, that looks a lot like the double angle identity for sine. Specifically, this looks like 1/2 sine of 2t. Because the double angle identity of sine of 2t would be 2 times sine t cosine t. So that means this is 0 to 1, with a 1/2. 0 to 1 of t sine of 2t dt. And this one, cosine squared t, I should be able to split that up into 1 plus cosine of 2t over 2. A half angle identity. So that'll give us 0 to 1. I'll have that 1/2, and it'll have t squared. And I'll separate that by itself. And then we'll also have another integral. Whoop, not t. That's just a 1. Of t squared cosine of 2t dt with its own 1/2. This minimal integral is pretty easy to solve. The other one's not so much. We're going to have to do some by parts here because I see an algebraic multiplying a trig. Both these look like by parts. This first one, not too bad. I could just say u is t, du is dt. dv is sine of 2t dt, which will leave v to be 1/2 cosine of 2t dt negative. So then that gives us 1/2 times negative 1/2 t cosine of 2t u times v. Yeah. And then we also have plus, because that negative there, 1/2 the integral from 0 to 1 of v du. So cosine of 2t dt. Plus this integral we can solve right now. That'll give us 1/3 t cubed. So that'll give us overall 1/6 t to the third power. And then the last one's also going to be by parts. However, this one's going to take a couple different steps. So what we can actually do is do a table for this one. So u and dv. The first u I'd set up is t squared, which would become 2t after I do the first derivative, and then would become 2, and then would become 0. So that's just me doing the derivatives all the way down. dv would be cosine of 2t. The integral of that would be 1/2 sine of 2t. The integral of that would be negative 1/4 cosine of 2t. And the integral of that will be negative 1/8 sine of 2t. And then that can expand. Remember to keep that 1/2 out there. We just have these diagonals. So we have 1/2 t squared sine of 2t minus 1/2 t cosine of 2t minus 1/4. I got 1/2 by 2 times negative 1/4, and 2 times negative 1/8 gives me 1/4 sine of 2t. Okay, so yeah, expanded pretty badly, but let's see what we can do here. Already we should see something that's pretty handy for us. Do we have anything here that we can work with? This actually should have, this should be a plus and then a minus and then a plus, and that minus will actually make this a plus. When we do the table method, so plus, minus, etc., etc. That would always go back and forth because of by parts, always going back and forth with plus and minus. That allows us to then take 1/2 t cosine 2t times 1/2. This and that piece will cancel out. And then this 1/2 cosine of 2t, that's going to give me a 1/4 sine of 2t. And this are going to be the same. So I'll do those in different colors. So that one and that one will cancel out. Which is pretty awesome. That means there's only a couple terms left. All I have left is 1/6 t cubed plus 1/4 t squared sine of 2t. This is evaluated from 0 to 1. 0 is irrelevant because they both have t in it, so it's going to cancel itself out. But if I plug in 1, I get 1/6 times 1 is 1/6. Plus 1/4 times 1 is 1/4 times sine of 2t, so that's 1/4 sine of 2. And that's going to be my answer for the area of this curve from 0 to 1 for t. So that's it. Now, this is one way that you could have solved this. There were other methods. For example, if you didn't do the table here and you just did by parts for the second one, after doing one version of it or one set of by parts, you'd actually find this first integral, but the minus version of it. So you could actually subtract from there. And all you'd have left are these middle two terms. So that would be arc length. Or that would be area. But now we need to find arc length. Okay, remember the formula for arc length here is, in this case, 0 to 1, square root of dx dt squared plus dy dt squared dt. So we need each of these. And we already have both of these. We have dx dt from before. We'll write it again. dx dt is sine t plus t cosine t. And dy dt was cosine t minus t sine of t. Means we have a lot of squaring here. So we have sine of t plus t cosine t quantity squared plus cosine of t minus t sine of t quantity squared dt. Like most that involve trig, this is going to expand a lot and then it's going to contract very quickly. Okay, if I square these, sine of t squared will give me sine squared t. Sine t times t cosine t twice will give me plus 2t sine of t cosine t, which we recognize 2 sine cosine as just sine of 2t, but we'll keep it as this. Plus t cosine t squared will give you t squared cosine squared t. That's the first piece. Just bracket so you recognize the first piece. The second piece will give you cosine squared t minus 2 times t sine of t cosine t plus t squared sine squared t. All right, initially we already see this piece and this piece cancel out. They're the same. So that already groups things together, and then we can group things together in terms of which ones have t's in, which ones don't. So we have sine squared t, and we also have a cosine squared t that does not have a coefficient of t on it. But the other ones have t squared on it. The other ones have t squared sine squared t, and the other one had a cosine squared t dt. So I just have sine of t and cosine t right here. And then let's do purple. T squared cosine squared t, t squared sine squared t right here, just with t squared factored out. I recognize this as 1. This is 1 because this is sine squared plus cosine squared is 1. So I have the square root of 1 plus t squared dt. And that could be a lot worse, considering. This is going to be a trig sub. We'll say that t is tangent theta, so we can stop writing t's. dt is secant squared theta d theta. 0, tangent is 0 at 0, tangent is 1 at pi fourths. And then we have 1 plus tangent squared is secant, times secant squared is secant cubed theta d theta. Now this you've likely had on your homework, or you can cite the back of the book if you want to use a formula for this. But what this will give you is secant tangent, or 1/2 rather. 1/2 secant theta tan theta plus 1/2 natural log of secant theta plus tangent theta from 0 to pi fourths. And again, you can say something like homework number whatever problem it was, if you just want to cite it. So you've already done the problem before. Probably. If I plug in pi fourths and 0 into this, secant of pi fourths is root 2, tangent of pi fourths is 1, plus 1/2 natural log of those same things, root 2 plus 1, minus if I plug in 0, tangent of 0 is 0, tangent of 0 here is 0, secant of 0 is 1, natural log of 1 is 0, so that's 0 plus 0. So we get a final answer of root 2 over 2 plus 1/2 natural log of root 2 plus 1. And that would be our final answer for the length. Okay. See how fun these problems are? Look how long they take. So that's an example of area. That's probably a more egregious one. And then arc length as well. Again, kind of egregious, but not too terribly so. All right. Let's do one more. This one we're going to find all three. We're going to find area, arc length, and also surface area. Now, in order to solve all these, area, arc length, and surface area, we're going to need the derivatives of each. Technically, for area, we don't need the derivative of y, but we are going to need it both for arc length and surface area. So let's just get all of these. We were balanced from 0 to 2. Okay, so we have x is e to the t minus t. That means the derivative of x with respect to t is e to the t minus 1. If y is 4 e to the t over 2, that means dy dt is 4e to the t over 2 times the derivative of the top is 1/2, so that's 2e to the t over 2. So those are the things I'm going to need to know for area and arc length and surface area. First, let's do area. Okay, so area is going to be the integral from 0 to 2 of y times dx. So 4 e to the t over 2 times e to the t minus 1 dt. That isn't too bad at all. The e to the t's multiply. We get 4 e to the t over 2 plus 1, really? So you can think of 3/2 t then. And then minus another 4e to the t over 2, or 1/2 t. Both of these are solvable. This one is going to multiply by 2/3, so we'll get 8/3 e to the 3/2 t. Minus this one's going to multiply by 2, so minus 8 e to the 1/2 t from 0 to 2. Therefore, we get as our answer for area, we are going to have to use 0, but if we plug in 2 first, 3/2 times 2 is just 3, so that's 8/3 e to the 3rd, minus 8 e to the 1/2 times 2, so that's just e. Minus if I plug in 0, e to the 0 is 1, e to the 0 is 1, so I get 8/3 minus 8. It's about as simplified as that can get. You can combine a little bit of it here if you want to. We have the 8/3 and 8, so you can say 8/3 e to the 3rd minus 8e. This would be 24/3. So that would give you negative 16/3 minus, so that's plus 16/3. So that would be our answer for area. Not too bad. Arc length and surface area are going to follow suit. They're not going to be too terribly long, but will take a little bit more algebra. Arc length is going to be the square root of each of these functions squared, or each of the derivatives squared. So e to the t minus 1 quantity squared plus 2e to the t over 2 quantity squared. If we evaluate each of these, e to the t minus 1 squared will give you e to the 2t minus 2e to the t plus 1. That'll be the first one squared. And the second one is just a singular term, so it'll give you 4 e to the t over 2 squared is e to the t. We combine some terms here. minus 2e to the t plus 4e to the t. That'll give you e to the 2t plus 2 to the et plus 1 dt. Notice that we had a minus 2e to the t when we had a minus 1 here. This one we have a plus 2 to the et. So this is going to actually split up as e to the t plus 1 squared dt. We had examples like this back when we did arc length. So this is really the integral from 0 to 2 of e to the t plus 1 dt, which is very easy. That's e to the t plus t from 0 to 2. So that'll give you e to the 2 plus 2 minus e to the 0, remember, is 1 minus 0. So that gives you e squared minus 1, or plus 1 rather. So that was our area. This is our arc length. So far, so good. We have only one more left. Surface area. Now, we haven't done surface area before, but it only works in some cases. Otherwise, you get to an integral that's not solvable. This one we can. We're going to have 2 pi from 0 to 2. We're going to have the function y, which, if we recall from above, our function y is 4e t over 2, times the square root of e to the t minus 1 quantity squared plus 2 e to the t over 2 quantity squared dt. Now the benefit of what we just did is we know that this is going to equal e to the t plus 1. We just did that square root in the previous problem. So this is 2 pi from 0 to 2 of 4 e to the t over 2 times e to the t plus 1 dt, which looks a lot more like the area formula that we did earlier. So that'll give us 4 e to the 3 halves t plus 4 e to the 1 half t dt. And we get really, this is the exact same formula as before. We had this one had a minus in it. So, small change. Overall, though, we get 2 pi. Don't forget the 2 pi. This one's going to multiply by 2/3, so we have 8/3 e to the 3 halves t. Plus this is going to multiply by 2, 8 e to the 1 half t. Evaluated from 0 to 2. If we plug in 2, we get 8/3 e to the 3 plus 8e. And if we plug in 0, we already talked about this, e to the 0 is 1, so that's 8/3 plus 8, where 8 is 24/3. So you get 2 pi times 8/3 e to the 3rd plus 8e, and this one's going to be 24/3 plus 8/3 is 32/3, so minus 32/3. And that would be our surface area. Now, if you want, you can do more than that. You can pull out some things. For example, we can pull 8 out of that entire thing if you wanted to, make it 16 pi. But at that point, there's no necessary need to do it. So we've done an example of both area and arc length that took a little bit of time, and we did an example of area, arc length, and surface area that don't take as much. But you get to see examples of all of them. Overall, they're the same concepts as we did with area, arc length, and surface area. You're still doing the integrals the same, just the formula is just a little bit altered. But you would still do the same kind of tricks. Notice what we did with arc length and surface area specifically. We were able to evaluate that as something squared and then take the square root out of that. Okay, if you have any questions, feel free to put those in the comments below, or ask your instructor directly. But with that said, I hope you have a nice day.